Okay, so it's a few minutes past 11 according to my time. I think it's appropriate for me to kick off the webinar. Firstly, welcome to you all to this this new format, or relatively new format for Specific, to present some of its research. We've already trialed it previously with interseasonal thermochemical storage, and now we're looking at aerospace and photovoltaic applications. So firstly, welcome. It's a relatively short webinar, so it's a bite-sized grasp of our scientific research that's been undergoing at Specific on next generation solar applications for aerospace. So you should get an overview of what we're doing, but of course I'd encourage you to get in touch with the individuals that are presenting if you've got any further questions or follow-ups or collaborations that you might want to engage in. So I'm just here for the questioning duties. I would like, if possible, for you to put your questions into the Q&A section, if possible. So this is the little section at the bottom of your page instead of in the chat function. That allows us to record the questions in a more straightforward way. What we'll do is, this is recorded, so there'll be an opportunity to access this subsequently. But also, if we don't get through your questions, we'll be able to access them, and we'll be able to talk and answer those questions and make sure that we provide a full collection of answers, even if they're not addressed during the webinar itself, which is, as I said, relatively short. So there's good opportunity for us to be able to engage via the Q&A session. And I'd obviously encourage you after today's webinar to get in touch with the team and talk more about it if it's something of interest. Ultimately, that's what we like doing as a science and engineering group. Okay, so enough from me. I'm going to transfer over now to Dr. Wing Chung Tsoi, who is leading this research and can give you the overview. So over to you, Chung.
Thank you, Trystan. Right. Can you see my slides? Okay, good. Right. So the aim today for me is to introduce perovskite solar cells for aerospace applications. It's a very new and interesting topic. And the solar cells are very simple. They just harvest light from space to generate power. And the main difference here is that the spectrum, the light spectrum in space there are more photons in the visible region, and even more in the UV region and the near infrared. And we call this spectrum, light spectrum in space, AM0 spectrum. And why we are interested on solar cells for aerospace? Roughly, it can be classified to two kinds of application. One is the High Altitude Pseudo Satellite, so-called HAPS. And this is an example of a commercial product from Airbus called Severe. And it's all covered by solar cells, all powered by solar cells. And it can be used for like communication and surveillance applications. And the other one is the real space application, like to power the satellite and for deep space mission, like this one to Jupiter. And traditionally, silicon solar cells is the first type of solar cell to used in space. And nowadays, the dominant type of solar cells for space is gallium arsenide-based multi-junction solar cells. And they are also expensive, right? Although better performance. So we are thinking about if there's any potential solar cell technology which has high specific power and low stored volume, or highly flexible. So specific power is the power generated per weight of the solar cell. So the higher the better, because it's very expensive to launch the solar cell, particularly to space. And the low stored volume is about the storage volume. So the lower, the better. For example, if you can make the solar cell highly flexible, then you can roll it up and then send to the space and then roll out. So in this case, you can save quite a lot of space. which means quite a lot of money as well. So why perovskite solar cell for aerospace? There are a number of very interesting properties for these perovskite semiconductors. The most important thing, one of the most important things is about the high specific power. So it has been reported that even for typical perovskite solar cell, it can has specific power about an order of magnitude better than existing inorganic solar cells for aerospace application. And the other thing is about the highly flexible feature because of the thin perovskite semiconductor, and it can be made on low weight flexible substrates, which means you can reduce the stored volume. And one of the challenge for perovskite solar cell is about the stability issue, which can be related to oxygen and humidity. But if you, for aerospace application, particularly for space application, there's basically no molecular oxygen and humidity. So the stability could be significantly better than on Earth. And last but not least, about the quality. So quality is more important than cost, particularly for the real space application. It costs a lot if you launch the solar cells and then it die within a couple of hours, right? You waste a lot of money. So it's more important for quality, which means we can use a little bit more expensive method to make the cell more efficient or more stable. So all of the work, Harrison, my postdoc, and Declan, my PhD, will present was undertaken at specific advanced university. And I would like to give my special thanks to Airbus and Diva Wales, which give the financial support for the work Harrison and Declan will present. And because of the support from Airbus and Diva Wales, we also got funding from European Space Agency and EPSRC program grant ATIP to carry out further work on perovskite solar cells for aerospace application. So I will now hand to Harrison to talk about our preliminary work on perovskite solar cell for HAPS application. Thank you.
Hi everyone. Can you see my screen now? Oh, I got some problem. Oh, yeah. Thanks for attending this webinar. So I'm Harrison. I'm working in Chung's group under specific, and today I would like to share the emerging PV technology, in particular, perovskite solar cell for HAPS application, as Chung mentioned. And oh, yeah. So what is HAPS? So HAPS is a new concept of using the stratosphere in the atmosphere. So we have several layers in the atmosphere, and above the normal commercial jet flight height, there is another layer called stratosphere, and this height is quite empty at the moment. So it's a good layer for us to launch some like aircraft, airplanes into this layer, and make good use of the this layer to make some like communication and also some surveying application using some aircraft. So at the moment, there are some examples of this kind of aircraft, some demonstrated by Alta Device, some demonstrated by NASA, and also some by Airbus. So this all kind of this device we usually call it a manned aerial vehicle, and also airship or maybe high altitude balloon can also travel in this stratosphere. And basically most of the aim is for the communication, navigation, and checking the climate or weather and environmental monitoring, or more importantly, maybe the military purpose. So now I will pick up an example and show you how they work. So this is an real example. This plane is called Sapphire, demonstrated by Airbus back into 2018. So you can see this is they're launching the plane into the air and using the solar power, and it can last for more than 1 day for the first time. So what is Sapphire is doing? So Sapphire is actually doing what I just said. It's for monitoring purposes and making connectivity to the world. So in some developing country, so some they don't have internet access, don't have broadband mobile data, so they need this kind of flight. They can provide some temporal internet connection to them, and with a low cost, and without building some very complicated infrastructure and building some emitter center. And also this kind of plane can also do some sensitivity work like weather monitoring, and also this can also be done for security defense purpose. So this is what Sapphire can do. And so to power such a plane, what we need is, of course, we need some power, and the power is obviously from the sun, because it has to be very lightweight. We don't have fuel inside, so we can only collect the energy by the sun. And so in Sapphire, they have a lot of solar panel on the plane and also on the body, and they can harvest light from the sun. And they have some battery for charging up, and it can last for the overnight flight as well. And the most important thing for this flight is the weight. So the weight is very important because in order to reduce the energy consumption. So this plane is only 75 kilogram. So it's only equivalent to 2 airplane seats. Yeah. So what we are doing now, we're exploring the performance of perovskite solar cell at HAPS condition. So we check the performance at -70 to 20 degrees Celsius. And also we particularly set the pressure at a lower pressure compared to atmosphere pressure to mimic the HAPS condition. And also we use AM0 spectrum, as Chung mentioned, above, because we are within the atmosphere, so the light is not filtered completely with the atmosphere. And the spectrum in the HAPS condition is more closer to the AM0 spectrum, so we use that as a standard for testing our solar cell. And on the right-hand side, this is a standard structure of our perovskite solar cell. And other than that, we also test the stability against the rapid temperature cycling from -85 degrees to 20 degrees with a ramping rate of 30 degrees per minute. So it warms up and cool down quickly to test the mechanical stability of like thermal expansion or during the rapid temperature change. Also, finally, we also test some operational stability to making some day and night shift operation. So here is the data. Surprisingly, so at room temperature or 20 degrees Celsius, the performance wasn't the best. And what we find is that when we cool it down to a lower temperature, and the performance which is maximum at around -20 degrees, which is very nice that because in HAPS condition, we are not always operating at close to 20 degrees. Instead, we operate at a rather low temperature between 0 and maybe -20 for the operational temperature. So this is a good sign for using this perovskite for HAPS application. And also, we find that the perovskite cell we have tested is very robust. So it can withstand rapid temperature change. You can see the black line behind is the change in the temperature. And the red point here is indicating that after several cycles, we keep testing at about 20 degrees, and the performance is still roughly the same. So no degradation, basically, against this rapid temperature change. And finally, we did some day and night operational testing. So although there are some degradation during the day, however, it seems that the performance can recover in the night, and then it drops again in another day. So you can see a lot of decay here, but even after 15 times, it can reach back to the original efficiency. So the stability should be fine for this kind of application. So that's it for my slide, and now I will pass the time to Declan for the space application for using perovskite solar cell.
Thank you, Harrison. Can we all see that? Is that all good? Yep, it's awesome. Right, so my name is Declan Hughes. I'm a PhD student under Dr. Wing Chung Tsoi. We're looking at the space applications for perovskite solar cells, and the talk I'm going to do today is focusing on work that we published in Solar Rapid Research Letters looking at the radiation stability for perovskite devices. So as a bit of like a preamble bit, when it comes to PV in space, there's a variety of uses: satellites, probes, the International Space Station, orbiting telescopes. As Harrison mentioned, a bit closer to ground, Zephyr project with Airbus, HAPS environment. But just because they already use solar cells doesn't mean we can get rid of the silicon, get rid of the gallium arsenide, and slap perovskite on them. There's a bit of there's a few prerequisites that need to be checked off before we can start adapting perovskites for space applications. As Chung mentioned, high specific power and efficiency is very important. But in terms of operating procedures, long-lasting stability is very important. The average lifetime of a satellite in an Earth orbit is about 5 years. So obviously perovskite need to be able to reach that to be able to be considered. And then thermal stability, photolight stability, radiation stability, and vacuum stability. Our group has looked at most of these, but for today I'm be focusing on the radiation stability. So now that we know what we're looking for in terms of satellites and in terms of orbiting characteristics, how big is space? So here we have several different types of orbits around the Earth. A low Earth orbit, which is where predominantly most of our work looks at, is about 100 kilometers to about 2,000 kilometers. And then within this pocket, you find the International Space Station, the Hubble telescope, CubeSats, Sun synchronous orbit satellites, and polar orbiting satellites. As you go further on, you enter medium Earth orbits, which is 2,000 to 35,786 kilometers. Here you find the Global Positioning System, GPS, and then high Earth orbit onwards is things like telecommunication satellites. Here, GEO 35786, the specific number is a global geosynchronous orbit, which is that the satellite in this orbit takes 24 hours to orbit the Earth. But most of our work focuses at the low Earth orbit end. So in terms of radiation environment at this low Earth orbit, there's two main sources. So because of the Earth's magnetic field lines, the Earth's magnetosphere, you get trapped protons and electrons in what's known as the Van Allen belts discovered in the 50s. These range from about hundreds of kiloelectron volts up to several hundreds of mega electron volts. And these are prevalent around the Earth at all times. And then other sources, which are a bit rarer, known as solar particle events, such as coronal mass ejections and solar flares from the sun. These range from kiloelectron volts up to gigaelectron volts. So and then an example here of a proton interacting with the atmosphere, becoming hadrons, neutrons, photons, and then electron scattering. So in terms of our work, the Van Allen belts are much more interesting. And here you have the inner belt and the outer belt, the image painstakingly drawn by our own Laura Penny. Here in the inner belt, you have a much higher energy range in terms of megaelectron volts, but you have a much lower fluence, which is the number of protons per unit area. And then in the outer belt, you have a much lower ion and electron energy, but a much higher particle fluence. So in terms of the work that we published in SonarRL, we looked at 150 kiloelectron volt proton implantation. This was in collaboration with University of Surrey, part of the Ion Beam Center. And we looked at 10 to the 12 to 10 to the 15 protons per centimeter squared for a broad range of different proton fluences. And we looked at the devices that Harrison showed for the HAPS work, which is the plain air NIP devices. So here, this is just a cartoon for ion implantation, which you have an ion source and then magnets used to mass separate and then focus the beam onto the target. So the work here, we fabricated our own devices, spin-coated triple cation devices. We replaced the more common ITO with AZO, making it more abundant and less toxic, no longer using the element, and we use quartz substrates, which reduce the effect of color centers, which are darkening of glass due to a radiation interaction with the lattice structure. We also tested devices at AM1.5G and AM0, obviously AM0 being more relevant for space applications. So in terms of the actual results for the work, we found at 10 to the 13, the devices are very stable. And then as you go 10 to the 14 and 15, the device performance decreases along with the JSC. So obviously our mindset was, why is this the case? So we looked at if it was the perovskite or if it was any of the transporting layers. We simulated the device structure, simulated the bombardment, found that most of the protons stop in the AZO. So we looked at the UV vis for the AZO and quartz. We found there was no change in relation to proton fluence. So there's no color centers forming, which is obviously good news. We also then looked at additional layer characterizations. We started looking at the spiro layer. We did Raman spectroscopy and photoluminescence measurements and found that as you increase the proton fluence, the PL drops, the Raman signal for the spiro decreases. So there's obviously an issue there with the spiro. So we needed to confirm this. So we did some work with Matt Carney's group, part specific. We did transient photovoltaics and charge density and found that as you increase the fluence up to 10 to the 14, the charge lifetime decreases, and we get a double length exponential fit on the TPV, which indicates interfacial recombination and increase of it. So with that, with the Raman data, we came to the conclusion that increased proton bombardment destroys the spiral layer. This leads to an increase in recombination, which leads to a decrease in device performance. So for a conclusion of this work, I believe this is still the case. We actually recorded a record PCE for AZO devices, 15% at 1.5G and 13.6 at AM0. The devices we've shown are stable up to 10 to the 13 at 150 keV. And then we showed that the spiro omatad is the defining factor which limits the device performance at higher fluences. And even at 10 to the 13, the device performance and stability is still higher than unencapsulated silicon, gallium arsenide, and 3,5 cells. So it's still very good in terms of results. So obviously from this work, acknowledge Airbus and Endeavour Wales for the financial support, and then AATIP project going forward. And then obviously specifics funders, the European Regional Development Fund and UKRI. And thank you for listening. Any questions? Let's be done.
Okay, thank you very much to the three of you for that great overview of the research. So I'd encourage any of our participants to put their questions into the Q&A. And we have one which has come up into the chat. So this is for you, Declan, and comes from Jenny Baker, our own Jenny Baker. Have you looked at the copper thiocyanate instead of spiro-omatad?
At the start of my PhD, I started looking at an alternative spiro, mainly for thermal stability. But one of the issues I found was getting a good device performance. There's a few papers out there that look at achieving, I believe there's a paper that achieved about 20% of CuSEN, but because of ion migration from the CuSEN in their paper, the gold contacts, and then the perovskite, they looked at an aluminium capping layer between the CuSEN and the gold, and a reduced graphene oxide capping layer between the perovskite and the CUSEN, and without those I couldn't get a very good device performance. So I at the time decided that maybe it wouldn't be the best course of action to proceed with it. But CUSEN is meant to be more stable, so I think if we could achieve a good device performance with it, then I think it would be a good idea to maybe look at the stability for CUSEN in terms of space applications.
Okay, thank you, Declan. I'm going to stay with you if that's all right, because I think I've got a question for you. You noted quite a lot about the degradation of spiral. Were you able to deconvolve whether there was degradation to the perovskite and in what nature was that degradation, or was it okay?
Yeah, so I didn't show it, but we did do XRD measurements for the perovskite and found that even at 10 to the 15, there is no change in the XRD peak intensity or position. So the crystalline structure of the perovskite remains unchanged. And this was from, rather than bombarding devices and then measuring the device, we bombarded perovskite film on just quartz substrates. So we looked at the perovskite itself as well.
Okay, thank you. We've got a question from Jason McFadden here. What efficiency do AM0 have in the climb phase? So perhaps this is one for you, Chung. What efficiency do AM0 have in the climb phase to the HAPS altitude, launch and climb to HAPS environment? This is actually a question that I'd thought as well. So great minds think alike. What happens during that phase? Is it important?
The efficiency for HAPS, the requirement for efficiency for HAPS.
Yeah, so I guess what efficiency does it have in as it climbs up? And also, are there any implications to the lifetime? That's an additional question for me as it climbs up and the pressure changes.
Yeah, this is more, I'm not the best person to ask, I'm not the engineer, but I get the information from them. So I think the state of the art actually have some 3.5 flexible solar cell already existed for the commercial product, which can have very high AM0 efficiency. I think about 30%. But the problem is extremely high cost. And this is one of the motivation why Airbus sponsors us for this, for using perovskite solar cell for HAPS application. And it's a good question. It point out not only to the specific power, but the absolute power as well. So that's why I think our future aim is also not only to improve the specific power, but also the absolute power, because the HAPS have a fixed area. So if we have lower power generation, we can increase the area. But because the engineer already designed with the fixed area, so it's very difficult to modify it, right? So I think this is one of the things for our future aim is also to increase the absolute power further. May not be 30%, but closer as we can.
Okay, sure. Thanks, Chung.
Yeah.
Okay, this is a question from Luke Ardolino, which relates to the product life cycle, I guess. Do you have to consider repairability in space applications, or is it just a case of replace what's broken? So what is the strategy when, say, it's coming to the end of its usable lifetime? Is it a case of the HAPS, landing and being replaced with a new one, or is there repairability options?
For the HAPS one, it's easier because it's not in the real space. It can come back. The good news. So I think, as far as I know, they can the lifetime requirement can be quite short compared with like the real space application, and it could be possible. I'm not sure, but it could be possible that you can dismantle the cell if required, and then put the new one on top. So I think that for HAPS application, there's more flexibility in terms of stability issue. Compared with like the real space one, I think you really need quite a long lifetime for typical application.
And I guess there's a question of whether the degradation mechanism of a perovskite in that environment is any different to one on ground level that allows the recycling or the life cycle sustainability aspect to be considered in a different way. Yes,
this is a good point. So we understand one of the challenge for perovskite solar cell is the stability issue, but the environment in aerospace or the HAPS environment or the real space environment is very different to the environment on Earth. So that's why we are studying like what Harrison mentioned about the mimic aerospace environment to look at the stability.
Mm-hmm. Okay, I mean, there are a number of, so this is perhaps one for Harrison. I mean, you mentioned perovskites and OPV. Is there a particular favored one going forward, do you think, or is the opportunities for both of them equally something that should be pursued?
So at the moment, in terms of efficiency, the perovskite definitely got a better position. But later, when I joined the Airbus project, actually my project is working on like combine the perovskite and organic as a tandem cell. So that in principle, they can be worked together, not separately. So it can be like, because the OPV side can absorb better in the infrared region compared to the perovskite one. So it could be an option. And also for OPV, the good thing is the stability is slightly better, and also do not contain any lead. So maybe better for manufacturing or the environmental issue.
And obviously the work on HAPS is a balance between weight versus efficiency. Where do you think the most opportunity for gains are? Is it in further reducing the weight, which seems challenging, or perhaps altering the active layer to be better performing, or is it to add weight and go for a tandem structure?
So to me, I think that like perovskite, the best efficiency already 25%, over 25%, almost 26%. And for the best efficiency for gallium arsenide devices, it's only 29%. So it's already very close to the maximum, even compared with other technologies. So efficiency-wise, I think that of course there's still room for improvement, but reducing the rate will be easier to have some breakthrough in terms of the HAPS or space application, because for inorganic cell, they still need some more robust substrate to build the cell. But for perovskite or OPV, you can build on some very thin plastic film, so which is something more. It's kind of a revolution to the technology, using like plastic substrate or very flexible substrate.
And I guess the relatively modest weight increase of going from a single to a tandem on a flexible substrate is a real opportunity for a gain.
Yeah, of course.
Okay, this is one for Chung perhaps, and comes from one of our attendees. Have you performed simple system level calculations on a HAPS platform, e.g. Zephyr, to determine the minimum required cell efficiency?
No. Yeah, we are not going to that. I think it's a good question, and practically we should consider this practical issue. But as you can see, what we present, we are more focused at the beginning about whether the stability issue is okay, and whether the efficiency one is okay at AM0. And then I think for future, this more practical consideration will become more important.
Sure. Okay. A couple more questions. In terms of materials used to manufacture the modules, have you considered if any of the components used are scarce or too expensive for commercial deployment, and how much will you need to reach that stage? So this is a common question for all photovoltaic manufacturing in reality.
Yeah.
So yeah, what are the components that you might consider problematic in terms of production volumes?
Honestly, I think Trystan, you're better than me to answer it. But I think the scaling up issue is a challenge, because like Harrison mentioned, it's 25% high efficiency, but I think it's a small scale one. So I think the scaling up issue is one of the future direction, and the cost. I think the material cost, if we can reduce it further, it'd be nice. Like if I think we use gold, so something more expensive material. If we can use cheaper one, it can help. And for the processing, I think it should be the attractive thing for perovskite. I think is the potential thing to make it low cost, right? Fully printable or coatable. So compare with like existing inorganic solar cell for aerospace application. Yeah, I think that's as far as I know. But Trystan, maybe you can add more.
Yeah, I mean, I think in terms of materials costs, perovskite does lend itself to being relatively low cost across the general material set. Some of the issues will come in ITO that might be used in the PET. Certainly evaporated gold, if you choose that as a contact. The scarcity of the materials is problematic, and that relates to the cost. Always one of the issues with flexible solar cells is the encapsulation. Now, an interesting question for you, Chung, is whether the conventional encapsulation that might be required on ground level for things like UV, for example, are they likely to be the same demanding encapsulation requirements in a HAPS environment?
Yeah, this is a good question as well, because the UV level in the AM zero spectrum, as I shown before, is about double amount of photons in the UV photons. So I think that you'll be more serious if the material is can be degraded under UV. So this is something we are going to study as well about the UV stability. And the other thing about the encapsulation is that nowadays we are mainly for glass substrate. We use glass for the encapsulation. For plastic, we use plastic. But if we can reduce the weight of the encapsulation, which can further increase the specific power, because the main contribution of the weight is from the substrate and the encapsulation.
Yes. Okay. So I think there is an opportunity to look into this, given that you're at a different environment. So I think, yeah, that's a great answer. Thanks. Okay, we've got a couple more questions. Another good one on it in terms of the way in which the devices are mounted. Do the PV substrates form part of the HAPS wing skin, or are they attached to an existing skin? So I guess the question is, are they built in directly, or are they post laminated?
As far as I know, I think it's laminated. Yeah, but I'm not the engineer for that, so.
Yeah, I would suspect that you would instead of depositing directly onto the wing material, that you would probably end up laminating.
Yeah.
Of course, direct deposition would save you one particular layer. I think the complexities are perhaps not counterproductive. So I think lamination would be the key.
Should be lamination, yeah, should be.
And additional challenges around adhesive strengths, and that's a glue expert's a discussion to have then, but an interesting one nonetheless.
Yeah.
This is another good question. I think I'm understanding correctly. How flexible do the PV cells need to be from a structural aspect? So when they're mounted, they're not really flexed, or are they?
Yeah, I think it would depend on the application. So for HAPS application, the requirement is just need to be able to match with the shape of the wing. So if the solar cell can still maintain good efficiency after certain bending, following the shape of the wing or the body, it should be fine. And I think perovskite has been shown to be quite good with high curvature, still maintain good efficiency. So it should work well. But there's another concept from Air Force or NASA a few years ago called ROSA, rolling out solar array. So they demonstrate that they use some flexible solar cell, which they don't disclose what is it. They just want to test the mechanism. So they send it out, and then they have the tubes to roll out the solar array, right? And then which can reduce the stored volume a lot. And so for this case, the requirement for the high curvature, I think, would be more strict, because it to roll more, like the toilet roll. Yeah. So you need to roll more compared with the HAPS curvature of the HAPS body.
Yeah. So in reality, there's no one single application for use of photovoltaics in space, and some might and rigid might be acceptable in some scenarios, but for this, it needs to form the shape of the wing, and that's key, I think.
Yeah.
Okay, I think we're coming to the end of the questions, and in fact coming to the end of the webinar. So, you know, in one final thing, I'd like to say thank you very much indeed to Declan, to Chung, and to Harrison for delivering a fascinating but brief, which is nice occasionally, insight into the research that's going on. Incredibly exciting, and something that we can see really, you know, growing and developing into the future as numbers go up. I'd also like to, I'm sure on behalf of the contributors, pass on our thanks to Laura Penny for setting up the webinar. It's very much appreciated for doing all the organization behind the scene. And last but not least, of course, to Airbus Endeavour and Airbus for the financial support that has allowed us to do this research in the first place. So I think for most of us, at least in the UK, it's lunchtime or coming up to lunchtime. So lovely to see the great talks today. And thank you very much to you all for attending, for the great questions. Thank you.
Thank you.